Okay. Uh, Good evening, everyone. Uh, my name is Syed Shabir Ahmad. I am a PMRF fellow and a PhD scholar in Department of Applied Mechanics and Biomedical Engineering, IIT Madras. So we are in this uh, course on finite element method and computational structural learning. Currently, we are in the week 7 uh, or the module 7 of the course, and up till now, we have seen various uh, techniques to go about solving and analyzing one-dimensional structures like bar and a beam, and then we went on for a more general case of 3D uh, systems. And from that, we have idealized to 2D systems, and we were looking into them in the last week. And also to remind that this course is taken by Professor Manish Pandit, Department of Earthquake Engineering, IIT Roorkee. So, as I said, we were dealing with uh, systems in two-dimensional domain in the week 6, and uh, we defined how can we discretize the two-dimensional domain, uh, and how can we get shape functions uh, for two-dimensional elements. We have seen a few problems and we have solved them related like questions like, which were relevant to the assignment. I hope you have already solved the assignment. So, and coming to the week 7, we have gone further uh, uh, into further defining map delay. So, till last week, whatever the structure which we have looked at, so they had like regular geometries. Like for example, uh, like this. If you have a geometry like this, you can define into you can divide this into elements like this: one, two, three, four, five. So here it is not so difficult to integrate in the element domain. Like while uh, you want to get the stiffness matrix and other traction related or force related terms, we have to obviously integrate on the element domain. So here it is not difficult because the domain which we have is a regular domain, and like we can use regular uh, elements which we have defined like a quadrilateral element, four-noded quadrilateral, eight-noded quadrilateral, or nine-noded quadrilateral, or triangles, regular uh, triangles. So we can divide the domain into uh, different simple elements like this, and we can do the integration, and then we can get the element stiffness matrix. And from that, we do the assembly, and then we get uh, uh, final structural stiffness matrix or the global stiffness matrix, and then we solve it to get the solution. So, but if we have some structure like uh, this, which has some geometry with curved boundary like this, probably I cannot like take square this uh, square or a quadrilateral elements or a triangular elements and discretize this curved structure because there will be some like discretization error. So, so what generally people do, or like in general, to avoid this discretization error, like this will be left out, this area will be left out while we take the domain of the element. So in order to do that, so we do like very fine meshing around this, like like very small elements, and very small elements are taken in this area. So even if I do this, like, so I will take like very small element like this. So a very fine mesh has to be used in this area in order to avoid, like, in order to reduce this uh, red red discretization error. Like, in order to reduce this, we have to take very fine mesh. So even though we do that, uh, like uh, there will be some discretization error. And if I want to do, like, if I want to make a very fine mesh, number of elements increases. So if I increase the number of elements, obviously the matrix stiffness matrix size and this total global stiffness matrix size increases. So that is not we want, because like we want to numerically, it will be a numerically difficult, it will be numerically difficult because like number of degrees of freedom increased and you have to solve a bigger system of matrices. So we can avoid that by using parametric elements. So if I have curved curved something curved like this, so if I take some mapping, which if I take some mapping which maps this, so this 8 noded quadrilateral, 1 2 3 4 5 6 7 8. So if I have this 8 noded quadrilateral, a uh, simple quadrilateral, which is, let's say, which has this domain -1 to -1 in eta and in meta. So this is the domain of this. And if I use, let's, some function of zeta and eta and meta, and like take so if I take some function of this domain and map to this, because this has three nodes, I can probably curve this and make this like this, curve this and make this like uh, and make this distorted element. So if I have this, if I somehow get this function f of eta comma eta, which is the mapping from the natural coordinate. So we call this natural system or natural coordinates. And this is our local or Cartesian coordinates, or the real system, or like a real element. So I take this element, and after taking this element, defining this element, uh, which is a proper square or a quadrilateral element, and I uh, define a mapping on this domain such that I get like if I take a function of this uh, take a function of this element and get this element, which is the real structural uh, geometry which we have. So then it becomes easier, and like we can avoid this uh, discretization errors, and we will be like, and also we can use improve the numerical accuracy, reduce the complexity computational complexity because like we don't need to like mesh like we don't need a finer mesh right now because we have defined like we have taken the elements as a curved or a distorted element itself instead of taking regular finite elements, and then we are using a mapping to map this distorted element to some regular element, so which is in natural coordinates, so eta and neta. Then probably not probably, it will improve our accuracy, discretization errors, and also the computational complexity. So that is what we did. So if we have some irregular domains or a curved domain or not like domains which are not regular, like this is a very regular shape, right? Like this is not we can divide it into elements having regular domains like proper quadrilaterals, but this has a curve. So here we cannot like here we cannot use this improper uh, domain because we will get discretization errors. So good evening, Surendran. Can you hear me? Hello. Uh, am I audible, Surendran? Uh, can you give me a thumbs up in the chat? Uh, can you hear me? Hello. Okay. Okay. So, uh, so that's why we can use this mapping and somehow avoid this discretization errors and also uh, avoid finer meshing. So and benefit from this parametric mapping. So we have seen that uh, we have seen this concept of parametric mapping detailed in this module of the course in a detailed manner in this module of the course. Uh, so we will solve some problems. So this will also help you in doing the assignment. So probably some like since we don't have any attendance in the class, like I hope you watch the recorded lecture on YouTube and get some help about solving these problems in the assignment. So, so here we have a four-noded quadrilateral element, uh, which is uh, given by this coordinate. So four vertices of the quadrilateral are given by this coordinate, and we have to find out the mapping, isoparametric mapping. So isoparametric means like we are using the shape functions for the solution And also we are also and we are using the same function for the mapping of the geometry. So if you have same functions for both geometry and the solution, then we can call it as a isoparametric mapping. So and there is also something called subparametric and superparametric. But in FEM, isoparametric mapping is something which we use. So probably till the end of this course, you will be using isoparametric mapping. So no need to worry about the other two. So and like we have to get the mapping, and we have to find out whether the mapping is valid for the element valid for the element to be chosen in the finite element analysis. So there are a few conditions like uh, whether an element can be used in the finite element analysis or not. So because sometimes the elements become too distorted, and they will not be suitable to take in the finite element analysis. So we'll see how we can uh, get that condition. So this uh, this is the element given. So I'll draw it. So this is 0.5 comma 0. Let's say this point is 0.5 comma 0, and the second point is uh, 2.25 comma 1.3, and the third point is 3.1 comma 2.7, and we have the fourth point P4. So remember that we always uh, define points in anti-clockwise direction. So that is something we do for numerical reason. So this is my for level. It will look something like, so this is an approximate figure of the quadrilateral. Okay. So as I said, like this is a not a regular quadrilateral, right? So I would like to make it into a regular, like I would like to have a regular quadrilateral. So I will use a mapping, parametric mapping, such that I will get a regular geometry quadrilateral, which which is like this. So here P1 will become minus 1 comma 1, and P2 will be 1 comma minus 1, and P3 will be 1 comma 1, and P4 will be minus 1. Okay. Good evening, Anish. Can you hear me?
Yes,
Uh,
sir. Good evening. I had a
Uh,
different place, so that's why I was late.
no, no, no problem. So, okay, just sum up till what we have discussed. So I was just discussing about. So till last week, whatever the problems which we solved, so we had regular geometrics like this, uh, regular geometry. So let's say this is some kind of a bracket or a beam column, something like that. This has a regular geometry. So I can take regular elements like this, quadrilateral elements. So like one, two, three, four, five elements which have regular shapes and quadrilaterals, and I can take them and do the analysis, finite element analysis in the in the Cartesian coordinates, whatever we have, the same coordinates we can use and do our analysis. But coming to this week, we are going into a deeper analysis for the cases in which we have curved geometry. So if you have a curved geometry, like let's say if you have a circle, you have a geometry with a circle like this. Your structure shape is a circular shape. Or let's say you have a uh, circular cylinder or something like uh, circular plate or something. So if you have something like this, probably like I cannot like let's say I cannot divide this into four elements. Uh, let's say like I'll divide it into four elements, like four triangles, four regular triangles. But the problem here is we are leaving out this part. So because like this part, so this is called discretization error. So we'll leave out this part because we are like just using four elements, regular elements. So we cannot include this part. So in order to avoid this discretization error, so what we do is we take more fine mesh. So instead of taking four elements, I'll increase the number of elements. So instead of taking four, what I'll do, I'll take more. Uh, I'll take a more fine mesh. Like probably I'll divide this into like this, like this, like this, like this, like this. So here, so here I can probably take a triangle, and here also I can take a triangle, small triangle. Here also I can take a triangle. So still you can see that there is some error here, discretization error. Something is being left out. Here also here also something will be left out. So at the like by increasing the number of elements, I am somehow reducing the uh, discretization error by taking a fine mesh. But what is the problem? Like if I have, let's say, if I had a lesser number of elements, I would have like if I had four elements, I will have a smaller stiffness matrix, right? But if I take number of elements like this, like I don't know how many elements are there, probably some hundreds of elements. Then this stiffness matrix size will also increase. So I have to increase the stiffness matrix size to in order to avoid this discretization error for this curved geometry or irregular geometry. So that is not something which is good computationally, because you have to, like, you will get a system like 1,000 stiffness matrix in 1,000 cross 1,000 or something like this you will get. So this is a bigger system to solve. Like I have, let's say, k u is equals to f. So I have to solve this system. So if I have to solve this, I have to invert a 1,000 by 1,000 matrix. So that becomes a numerically challenging part. So that is like, so even though I'm increasing the number of elements, I am I am making my problem even more difficult to solve because I am using a finer mesh. So instead of this, can I do something else? So which can avoid a bigger system, like which can, instead of 1,000 by 1,000, if I get 10 by 10, and like solve the problem in a easy manner without this numerical complexity, with a bigger matrix size of stiffness. So that can be done by parametric mapping. So in parametric mapping, what we do is, like, if I have a curved curved element, like, or a curved geometry like this, I can I can map this curved or irregular geometry to a regular geometry using some function. Let's say that function is f of eta comma neta. So mapping is nothing but function, like a relationship between two things. So this regular quadrilateral, eight-noded quadrilateral is defined on the natural coordinates. So natural coordinates are basically eta and eta, and they are like, and this element has the domain -1 to +1 in both these coordinates. So if I take this, if I take this, and if I take this natural coordinate element and somehow distort, like if I move this nodes of the natural coordinate, I will get a curved geometry like this, because this has three nodes. You can and this has a like, if I have three nodes, like last week we have seen that we'll get a uh, what do you say, second order shape functions, right? Second order shape functions. So n1, n2, n3 will have square terms. So if I have a square term, it means like we can probably, like, square means like you can polynomial with degree 2 can be used to define a curved uh, can be used to define a curve, right? Like parabola or something, circle. So these have square terms. So somehow I can like I can distort this by using some function and make this natural coordinate, regular quadrilateral, into a curved element like this. So if I get this function, so which maps from natural coordinates to Cartesian coordinates. So life will become easier. I don't need to make I don't need to take a lot of elements. Instead of that, I can take curved elements only or irregular elements only, and then map it to some regular elements. And using that mapping, then we can do all kinds of further steps, like getting the stiffness matrix, and then also getting the boundary terms, everything in terms of the natural coordinates, and finally solve the problem. Like instead of solving 1,000 by 1,000, like you can solve instead of solving 1,000 by 1,000, like you can just take the circle and divide it into uh, like, let's say, four elements, and you can take this as one element, this as one element, this as one element, and this as one element. Four elements, and you can get a much more uh, simpler solver, so problem, simple problem, because you have now, let's say, one, two, three, four, five, six, something like this, like uh, lesser number of nodes, lesser number of nodes. So you'll get probably a 10 cross 10 or some simple system. So that's why we have to use, that's why we can use parametric mapping to avoid this complexity when we have irregular domains like curved domains or some irregular, other irregular domains, and make our life much more simple. So we have some problems related to parametric mapping in this module. So in this assignment also, seventh assignment, so similar problems we will see. So let's say you have a quadrilateral, four-noded quadrilateral element, which has some like distorted geometry like this. Even though this is a regular quadrilateral shape, but this is distorted. You can see like this is not a perfect 90 by 90. Like all the sides don't are not making 90 degrees angle with each other, right? So this will also be a challenging uh, problem to solve. Like if you are directly taking it, like you have to like when you do the integration, you might get some complexity, but like yeah, that's not a big problem compared to the curved uh, part. But yeah, like we will see how we can map this distorted quadrilateral to a regular quadrilateral in natural coordinates, which looks like this. So this is a regular quadrilateral, or this is a square actually. So this is a square, simple square. And if I can get some mapping F, so which relates this square to this distorted quadrilateral, then my life will be simpler while doing the finite element analysis. So we'll see how we can do that. So first we should define the shape functions in natural coordinates. So we are taking the shape functions in natural coordinates. So in natural coordinates, the shape functions for a four-noded quadrilateral can be given as 1 by 4, 1 minus beta into 1 minus neta, 1 n2 into 1 by 4, 1 plus beta to 1 minus neta, n3 into n3 is equals to 1 by 4, 1 plus neta into 1 plus neta. N4 is equals to 1 by 4 into 1 plus 1 minus beta into 1 plus beta. So here, uh, this is a simple thing like these are regular Lagrange shape functions like we have seen, right? So we can just take uh, x instead of eta, you can take x minus xi, x minus uh, x1, x minus x2, so y minus y2 divided by y1, x minus x2 divided by y1, sorry, y1 minus y2. So instead of x, instead of x, we'll just take here eta. So instead of x, you can just take eta, and x1 is uh, uh, here we have x1 is minus 1 comma 1. So for that we'll take uh, we'll we'll get plus 1, and we'll get eta plus 1 divided by uh, this is x1 is sorry, this x1 is x1 is 1 here, and y2 is also this is also 1. So we will get minus 1 minus 1 minus 1. So this is how we get. So this is a simple thing. Lagrange shape functions we have used. We have defined how we can define Lagrange shape functions. Probably you can refer to last week's nodes, and you can get this shape function. So these are the shape functions in natural code. So in isoparametric formulation, so geometric mapping. So these are the shape functions which we used for these are the shape functions which we used for solution approximation. So u of x1, xy, comma y is equals to n1 u1 plus n2 u2. So u1, u2, u3 are the nodal displacements. So nodal displacements in x direction, and v of x comma y similarly is n2 u2. So n1, n2, n3, n4 are shape functions. So they are not like constants; they are shape functions. v3 plus n4 v4. So these shape functions which we used for solution approximation, we will also use this shape function for the parametric mapping. So that's why this is called isoparametric mapping. You are using the same shape functions for displacement or the solution approximation for the geometric mapping. So in isoparametric in isoparametric formulation, geometry mapping is done by the same shape function shape functions used for solution approximation. So now we have the shape functions. We have to get the mapping. So you yeah, mapping is nothing but you have to get the relation between x and xy and theta and theta. So let's say you have some point x comma y in the regular domain, and you can use this you can use this interpolation to get that point from the coordinates which we have. So because we have a four noded quadrilateral, right? So so the first point coordinates are x1 y1, and the second point coordinates are x2 y2, and the third point quadrilaterals are x3 y3, and the fourth point quadrilateral are x4 y4. Okay. So so is the quadrilateral. So this is x1 y1. This is x1 y1. This is x2 y2. This is x3 y3. This is x4 y4. So if there is any point x comma y, you can get that point x comma y from these points using this interpolation. So okay, so this is the mapping. So but here we have taken the shape functions which are in this coordinates, natural coordinates. So what we'll do is we'll simply take this shape function and substitute in this triangle which we have. So n1 is equals to 1 minus eta in 1 by 4 into n 1 minus eta 1 minus eta. So similarly n2 n3 n3 n4 all these things we will substitute, and also we will substitute the values of x1 x2 x3 x1 x2 x3 y1 y2 y3, and Here, substituting here x1, all the values of the coordinates up to x4 and y4, and substituting the shape functions which we derived for natural coordinates, we will get, and after multiplying, we will get xy is equals to 5 plus, sorry, 5 neta plus 75 into theta plus 29 neta plus 139 by 80. And this is minus 3 neta minus 10 theta minus 17 neta minus 30. Sorry, this is not, this is just multiplied by this 5 neta plus 7. Is minus 3 neta minus 10 theta minus 17 neta 35. So this is the mapping I have got. So if I know a point, if I know a point, some point in this, if I know some point in this, and like after I distort this into this shape, and I want to know what are the uh, what are the coordinates of this point in xy coordinate. Let's say P is the point, and after you distort this regular geometric shape square in natural coordinates to some kind of parallelogram shape, after you distort, you want to find out where this point is lying on this parallel. Then you can substitute the values of eta and neta, and you can get the values x comma y, so which is in the regular. So this is the mapping. So mapping is nothing but relationship between x and y and eta and neta. So if you sub, if you just do this, you will get the mapping. So so we have got the mapping, and the main condition, like if we can use this mapping for finite element analysis or not is also asked. So if we can use this mapping, whether the mapping is valid for the finite element analysis, that is what the question also asks here. So just finding out the mapping is not enough. We have to check whether this will satisfy. So for that, we have seen that there is a condition, so that we have to find out, like if you want to, let's say, find out the stiffness matrix and also some other matrices in natural coordinates, you will get a Jacobian term. So Jacobian, so which is J is equals to, so when you convert from Cartesian coordinates to natural coordinates, you will get this Jacobian as extra in the integration, something extra which you get in the integration. So this Jacobian we have to find out, and like let's say because you have got x is equals to this, y is equals to this, and if you do this uh, division, you do this differentiation with theta, uh, you will get the Jacobian. So which is theta plus theta plus 15 by 80, sorry 16, 16 minus 3 theta by 70 by 20, and 5 theta plus 29 by 80 and minus 3 eta minus 70 by 20. So this is my Jacobian. So now in the stiffness matrix, like you will get something like this. So g of something eta and eta, and in addition to that, you will get this Jacobian, determinant of Jacobian, and d eta d meta. So this determinant should not become zero. So if this determinant becomes zero, then the stiffness matrix term will become zero. So that is not something which we want. So if the mapping is valid, like if the mapping can be used for finite element analysis, like for that condition, this determinant uh, should should not be equal to zero. So that is the condition which we have to uh, make sure that it satisfies. So determinant cannot be zero. So determinant of J cannot be. So and also sometimes you need to do the in some cases you will also need to do this inverse of J. So if J is having if J is like uh, if J is having determinant zero, then J is not invertible. So that's why like it becomes essential that determinant should not be zero, and we have to avoid the mapping which like uh, which makes this determinant zero in our domain. So we'll check. So here that J will become, and we'll also make sure that this is always greater than one. Determinant is greater than one. That is also one condition which we want to impose. So that J will, like if you do simple determinant operation, we will get 275 eta minus 172 meta minus 985 divided by 16. So we will find out when this determinant will be equal to zero. So let's put this det j is equals to zero. So if you put if you take det j is equals to zero, so you will get 275 eta minus 172 meta 985 by 1600 is equals to zero. So by simplifying this, you can get neta is equals to 275 eta minus 985 by 172. So this is a relationship between x and y, right? So you can probably write this as y is equals to mx plus c. So here y is neta and x is eta. So m is nothing but you can write 275 by 122. C is nothing but minus 985 by 172. So this is a equation of straight line. So like this straight line, like if you draw uh, this straight line, if you draw in the you're drawing the natural coordinate system. So let's say this is my natural coordinate system, and this is my element. Okay, this my element is there from this is eta and this is eta. Okay, so this is my element in the natural coordinates. Let's say this is zero. Here this is zero, and here it is minus one, plus one, or this. Let's say this is eta and this is eta. This is eta. 1, 2, 3, 4, something. Goes. This is -1. This is +1. Uh, Similarly, this will also have. So, so if I draw this straight line in eta is equals to something, so this straight line will be this straight line. Straight line will look probably yeah, straight line. Like this is lying in this area in the domain, area in the natural body, and this is my shape. This is my quadrilateral. This is the domain in this is the domain of the element in the natural coordinate. So this straight line is lying outside my domain. So the region in which delta j is equals to 0 is not in my domain. So there is no problem. So delta j is not becoming 0 in my domain. So that's why I can use this mapping in my finite element analysis. So the mapping is valid. So that's how I can say that this mapping is valid. So that j will not become 0. So or another way to check this is like drawing the line and checking. Just put just take some points in the domain and check like all the points. Like randomly choose points between -1 to +1 of eta and eta and check. So if that j is becoming 0, if that j is not becoming 0, then your mapping is valid. If that j is becoming 0 in your domain, then your mapping is invalid and you cannot use it for finite element analysis. So that's how we check it. Let's say if you have another quadrilateral, you have another quadrilateral, and the shape of this looks like this. If you draw it this is the shape of the quadrilateral. Okay. So this is some quadrilateral which has P1 is equal to 0.5. Second point is this 1.2, 1.3. The third point is 3.1, 2.7, and the fourth point is 1.1. So this is the quadrilateral. Okay. Now, obviously, this is a distorted element, not a regular geometry which we want. So we can define a mapping which maps this distorted element to a regular square four-noded element in the natural coordinates. So which will look like this. So P1 here is -1, -1. P2 here is 1, -1. P3 is 1, and P4 is -1. So I have to get the mapping which takes this normal quadrilateral and distorts this quadrilateral in this shape. So so you will do you will do the same thing. You will get the shape functions in natural coordinate. The same thing what we have done for the previous problem. So after getting the shape function again, we will get this mapping. So you will get some uh, something in terms of eta and eta. Here also something in terms of eta and eta. Some function you will get. Let's write it test gn. Okay. So then after that we have to get the Jacobian. So after you get the mapping, You have to get this Jacobian. X by neta and y by dou y by dou neta. So after you get this Jacobian, you will get uh, the Jacobian like this. 10 divided by 20, 13 theta plus 25 divided by 40 minus 3 theta minus 17 divided by. So this is my Jacobian. And again, I have to uh, get, I have to see, I have to get the determinant of Jacobian. So Jacobian's determinant is this. So I want to find out where this Jacobian will become 0. I'll put that j is equals to 0, determinant of Jacobian, where I want to find out where this determinant of Jacobian is becoming 0. So, and make sure that this region doesn't lie in my domain of the element. So that j will be 0 if I get that j will be equal to 0, then you will get something like uh, this 211 meta plus 296 meta plus 209 is equals to 0. Then you can get this as minus 211 eta minus 209 divided by 296. So this is the straight line on which determinant will become 0. Okay. So now the same thing. I will draw. I will draw the domain. So this is my natural coordinates system, uh, and my my element is here in the natural coordinate system, so which has the domain of -1 to +1. So this is 0 plus 1 minus 1 again, and this is 0 and this is 0. So this is neta and this is theta. Like xy axis, we have theta and neta. So this is 2, 3, 4, something like this. And this is my domain. This is my domain. Regular quadrilateral, square quadrilateral. And if I draw this line, neta is equals to -211 eta -2096. This line will start from here, intersects x-axis and some y-axis somewhere here, and this will pass through the domain like this. Okay, so this is the line that j is equals to 0. So you can see this whole line is the region where that j is becoming equal to 0, and this region is also lying in my element domain. So my element domain is this quadrilateral. So in the element domain, the Jacobian is becoming, the determinant of Jacobian is becoming equal to 0. So that's why I cannot take this mapping for my finite element. So I cannot take this element. So you can see like this element is very distorted. So this happens. This happens in the cases where, like, if your element shape is like very distorted like this, then you will probably have a chance that your determinant will become 0. in the domain. So determinant of Jacobian will become zero. So that's why we don't take these kind of elements in our finite element analysis. So this kind of very distorted shapes, like you will see, like if you have a very distorted shape like this, there is a high probability that you will get that j is equal to zero. So the mapping here is not valid, and like we cannot use it for finite element analysis. So that is the conclusion. So uh, that's how you can check if the mapping is valid or invalid. So this the multiplications which I have done, uh, like you just have to substitute and get this also, like it's very simple, like it's not a very big thing, like, and also as I said, you can also use uh, MATLAB or Python to do this multiplication, which will make life easier a bit. So you don't have to go and do like long calculations using your hand. Uh, Anish, is this clear? Like, do you have any doubts in this? Uh, Whatever which we discussed.
So the theory is fine for me. I will do it calculation and I will check.
No, no. Yeah,
Sir,
can you say it again? Mm.
yeah, I understood the theory part. The calculation part, I will try it and see.
Ah, okay, okay. You understood why determinant should not be zero. That thing you
Yeah,
understood, right?
and about the isoparametric mapping and all.
Yeah, you have understood why we do the mapping.
Yeah.
Yeah, then it's fine. It's great. Okay. Uh, we have uh, okay. Now we'll do one thing. Uh, I'll show how we can use Python for doing our calculations. So I have two simple. I've I've solved the last week problem, and there is also first week. There is also like this week's problem. I think the second problem in the assignment. So that also have written, but I won't run the code and show. But like the last week problem, we'll see how we can use Python to our advantage and do like very complex problem. Like this is still element level analysis, but we'll see. Can you see this screen, Anish? Uh,
Yes, sir. One browser. The PPTC.
okay, okay. So, mm, Uh, no. Yeah, using. I think this is all. So, all I think states. So, okay. So in the last week, we solved this problem. So in which we defined like we wanted to get the shape functions uh, for a nine-noded quadrilateral and also for a eight-noded serendipity uh, uh, quadrilateral. So we wanted to get the shape functions for both of them. So this we are using like here we are using and doing symbolic calculation. So like at the end we have to get the shape functions in terms of x and y, right? So if you are doing some calculations in terms of x and y, you will get the shape functions. Uh, like if you are using the symbolic calculations, you will get uh, the shape functions in x and y. So n1, n2, n3, n4 till n9, you will get uh, in the simple shape functions, which we have got here. Okay, so first we will get like we have this like quadrilateral which has nine nodes. Okay, so all the nine nodes, the coordinates of nine nodes are given here. So first, like if I want to do symbolic calculations in Python, I have to have this library which I have to install. So the library, the name of the library is SymPy. Okay, so if you want to use Python uh, and like and all the libraries are installed, so you can use Anaconda distribution. So you can go to web, like you can go to the internet and you can download Anaconda. So the if you download Anaconda, you will get all the things installed. Like you will get Jupyter Notebook, and also you will have Spider, like another like different kinds of environments which you can use. Like I like prefer using Jupyter Notebook because I like it. Like this is very easier to use. So And also to do symbolic calculations, it is useful. So Anish, you use Python, right? You use Python or MATLAB? Uh,
Sir, I don't have experience in both.
both
Just
both you
C++.
don't have. C++ you have. Okay, okay. So yeah, so like you can just go and search how to install Anaconda. Like you will get thousands of videos. Like you, and after installing Anaconda, you can go to, like, after you have installed Anaconda, you can go here Anaconda, uh, search in the start menu. Uh, or probably this is not visible. I'll just share again. Yeah. Yeah. So like let's say you can go and search Anaconda. So if you go and search Anaconda, so you can see here, you will get anaconda.com or Anaconda here. You can see like anaconda.com. If you go to anaconda.com, you can see here Anaconda free download. So you can click here free download. Free download. If you click, where is it? Download. Yeah. Here, if you click get started, you have to get registered with email something. I won't do that, but like you can just go and install it. So you can just download it. But this is asking keep registration, right? Yeah, keep registration. Yeah, see, you can see there is like Anaconda and also there is also Miniconda, but you can directly install this uh, Anaconda. So you will get the latest uh, Python version, which is Python 3.13. So you can just click here download, and after you download the file, you can go to that file and you can install Anaconda. So so that is how you install Anaconda. And after you have installed, you can go and search here. Uh, in the start menu, you will get this Anaconda prompt, or like you just go to Anaconda Navigator. Click on Anaconda Navigator. So if you click on Anaconda Navigator, you have to probably will be not open. Yeah. It's opening. So the advantage of using Anaconda, like installing Anaconda, is like it will have all these libraries, SymPy, NumPy, like whatever. Like there are a lot of libraries in Python, so we can directly use those uh, all these libraries. So like you don't have to like install all this. So you can see here there are a lot of apps in Anaconda which are already installed. So if you are like if you if you don't want to like go and like install Python first, then you install all the libraries first, then you install some kind of notebook to write a code. So if you want to avoid that, you just go like install Anaconda. That will be a very easier thing to do. Like all the most used libraries will be there. So in this, you can also see there is Jupyter Lab. That is also as like some kind of environment to write code. And currently, like as I've shown, we were using the Jupyter Notebook. So Jupyter Notebook is there, Jupyter Lab is there. These are like similar kind of notebooks, and there is also Spider. So Spider is also some kind of code writing environment which people use. So this is like very similar to Python. Sorry, MATLAB also. Like if you, I'll just open Spider. So if I click on Spider, yeah, it's launching. Opening. Yeah. So this is how Spider looks like. So in this you can write code, and here you can see all the like all that like uh, all that like variables which you save. All these things you can get. So here you can write code. So like this is saying so 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 if you can like get a good introduction of this is the editor, code editor, and this is the Python console. Like you can give commands and run here. And this is the variable explorer. Like if you have defined some variables, x is equal to something, y is equal to something. So all this will come here. So help is also there. If you want any like plots will come also here. So if you have any plots, what are the files, different files which you are saving in the code. So all these things can come here. So this is Spider. Like I don't use it, but you can like if you are someone like if you want uh, Python like sorry MATLAB like environment, you can use Spider. But I don't prefer using because I like Jupyter. So this is Jupyter Notebook. This is also an environment. So Jupyter Notebook will open in some kind of browser. So like here, this is opening in Microsoft Edge. So you can like also open using uh, like whatever the default browser you have, it will open in that. So this is like HTML app. This doesn't have a separate app like Spider. So Spider will open like a separate app. So just close this. So here, as I've said, so like the basics of writing code is like whenever you're writing a code, like you have to import all the libraries which are required in the code. Okay. So we are defining a shape function for a 8 node quadrilateral and a 9 node quadrilateral. So like we want to get the shape functions. We want to derive what are the shape functions for that. So and in XY coordinates. So X and Y are the symbols which we are using. So we have to define X comma Y as symbols. So in order to tell the computer that X and Y are symbols, so you have to use this command sp dot symbols X comma Y. So X comma Y will be considered as symbols from now on. So then after that you have the 9 nodes. First I want the 9 nodes for the quadrilateral. So all the 9 nodes are defined here. So these are the 4 vertices of the quadrilateral, and these are the middle nodes. So SP rational 3 comma 2 is nothing but 3 by 2 is written. 3 by 2 can be taken as 3 by 2 can be written as like this. So SP dot rational 3 comma 2, it is nothing but 3 by 2, because we are using the symbolic calculations here. Like we have to do symbolic calculations. So we have to define the rational terms. So, or the rational numbers, like the numbers which are in the form of X comma Y, X by Y have to be defined like this. So this is one point. This is another middle point on the edge, and these are middle point, and this is the point at the center of the quadrilateral. So which lies on the center of the quadrilateral. So all the 9 nodes we have defined here. Similarly, if I have a 8 node at quadrilateral, what I will do is I'll just remove the last point. So this is an operation like you can run. Like this is an array operation in which like I'm just taking all the elements up to in this array in the array nodes Q9. I'm just taking elements up to this, and I'm removing this because I don't want the central point in the serendipity element. So that's how I can define like that. And then I have to define the basis. So I have to take all the polynomial terms which are possible, taking 9 points, right? So we know that we have seen the Pascal triangle. So for the quadrilateral 9, so I have to take this all the basis terms which we require, which is 1 x y x square x into y square x square into y, and x into y square. So in Python you can see, like if you want to define square, like you have to uh, use this double star uh, uh, double star like this. So in MATLAB, it is just a caret symbol you use, x power, like whatever this is, simple uh, power symbol which we use, superscript or power symbol which we use, that is used in MATLAB. But in Python, for power, you have to use 2 stars. So this is the symbol for power in Python. So these are all the terms which will lie in the these are all the terms. These are all the basis terms which will come for the 8-noded for the 9-noded quadrilateral. For the simple for the same 8-noded quadrilateral, these are the 8 terms. Like uh, we will get rid of this last term here. So we will get rid of this last term. So these are the basis. So for each point, like I have to like for 0 comma 0, and for 3 comma 0 3 comma 4, if I substitute the values of x and y, I'll get a coordinate matrix C, which we have already seen, like how that goes. But this is just defining the basis which we need, like polynomial terms which we need. And then we have to build the shape functions, right? So we have to get the shape functions. So I'm using this code, which is not, this is called a function. So function is something which you define, like if you want to run the same code multiple number of times, like same block of code multiple number of times, you can define it as a function and call that function multiple times in your code, and do the same evaluation. You don't need to write every time these lines of code to do. Like I will define this function. The name of this function is build shape functions. Okay. So if I have the nodes, so these are the nodes. If I have the nodes and also the basis, so after I'll give the nodes and the basis as the input for the function, and then after that I'll get the shape functions. Okay. I'll get the shape functions for the quadrilateral, whatever which we are getting. So in this function, you can see that we have defined a matrix. So sp dot matrix is a symbolic matrix. So for all the points, like this is nothing but the coordinate matrix C which we have given. So this is doing just that. For each point, you will get the evaluation. So 1 x1 y1 x1 square y1 square x1 y1. So and then for x2 comma y2, like this will build that coordinate matrix. So this is doing that. This line is doing that. And then obviously I need to get the inverse of this. So and then I have to get like after I have the inverse of the coordinate matrix, I can get the shape functions. So we have seen like that is nothing but 1 xy square into C inverse into x1 y1 x2 y2 x2 y3. So we know how we have done the calculations. So that is done by this code. So for each node, I will get a matrix and like define a matrix for the uh, calculations. So inverse of A into EI. So EI is nothing but my uh, okay. EI is nothing but my coordinate matrix. So we will just show this. So this I think we had okay. It's not there. So we want to determine the coefficients like A naught, A1, A2, A3. So that can be done by this simple calculation of inverse of C on the coordinate matrix into this matrix, which is nothing but our uh, uh, like wherever there is uh, uh, I and J, or like wherever there are points, like you will get one, and then wherever there is like uh, there are no if wherever there is J is not equals to one, it will give zero. So then after that, I have to take this coefficients and multiply with our basis which we have defined here. So basis. So and coefficients into basis is nothing but the polynomial which we get. So for each shape function, you will get some polynomial. So this will just simplify. Like if you have a large expression, this will just simplify. So then after that, you will share each shape function. Like uh, because there are n nodes. Like first, you will find out for the first node, second node, third node, ninth till the ninth node. This for loop will run, and you will get all the shape polynomials. So I'll just uh, I'll just split this. You can split this cell. Okay. So I have defined this function which builds my shape function, and also then after that I'll use this function to get the shape functions for my 9 node at quadrilateral. So if I give uh, nodes Q9, which are the nodes for the 9 node quadrilateral, and the basis for Q9 uh, as the input of this function, it will build the shape function and it will give me the coordinate matrix and also the shape functions uh, which are required. So let's say I'll just restart this kernel, like because I have already run this. So I'll just restart and I'll run this. So you can see that this start mark is there. It means like this is running. Now it has completed running. So then I have got This I have run, and I have got like successfully saved this shape functions uh, here in this, and also the coordinate matrix for the each quadrilateral has also been derived. So let's see how my shape functions are. So shape Q9. So this will give all the shape function for the nine noded quadrilateral. So this shape functions, this matrix, this array has nine elements. So let's say I want n1. So I'll just take the first term. So this is I'm just extracting the first term from this array. So you can see that this is printing beautifully because I'm using Jupyter Notebook. So mathematically, it is uh, like easier to see and verify. So if you're using Jupyter Notebook, this is the main advantage. So this is my first shape function. So and if I want the second shape function, this is my second shape function. So like in Python, indexing starts from zero. So that's why I'm like for the first shape function, I'm using zero. For the second shape function, I am using one. So if I want the ninth shape function, n9, I have to use 8 here. So this is my ninth. So like this, I can write a code like instead of like 9 cross 9 matrix, inverting the 9 cross 9 matrix easier here because you are not doing it, a computer is doing it for you. So and you can use Python for your advantage. So this is the same thing, like this block is also the same thing. I'm just printing all the shape functions for the 9 noded quadrilateral and the 8 noded quadrilateral. uh, but yeah, so because I'm using the symbolic uh, calculations, I have to use this library SymPy here. So SymPy is a library which, by using which, you can use symbolic calculations in Python. So that's how you can use Python or MATLAB, whatever the language which you prefer for your advantage, and code and get the answer. But I have written this code by using like help of ChatGPT. But I would suggest you please don't do it because I can write this code from scratch even if I don't use ChatGPT. So because I have already done courses on finite element, two, three courses, like different courses related to that. So I can be like I can like I know each and every line which Python is giving, like which ChatGPT gives me. I can verify if this code is correct or not. So I can like I know like what it is doing in the each step after it gives the code. So I can use ChatGPT. But you don't use it because you are learning still. So you have to write your codes on your own. So that's what I would suggest. Okay. It's not a simple. It's uh, it's simple problem at first, but if you do like you do right for one or two uh, problems, you will get it easily. Like it's not very complex. If you learn SymPy, NumPy, there are some libraries in Python. If you know learn these libraries, SymPy, NumPy, and SciPy, these are three libraries. I think it will be very helpful for you. Like if you use them, then you can solve any problem like without any difficulty by coding. So instead of doing by hand, like it is like probably impossible to solve problems by hand if you have some bigger systems. Uh, like in the next week, probably in the next week, we will solve a very bigger problem, which is like some 100 by 100 elements. Like then you will get a matrix which is like which has a size of thousands, like some thousand cross thousand or something like that. Uh, then coding is something which we have to use. There is no other option. You have to code and solve these problems. Finite element method is meant for computers. So that's what it was derived for, and that's what it was invented for in the first place. Like you can, we can solve the problems using computers. So that's why. it is very helpful to use computers or coding, or whatever the language you have. You have any questions? Okay, so this was also another problem from the last. Yeah, this was the problem from the last week's assignment. Yeah, yeah, this problem we had, right? So, so this is a uh, element which was given, and this plane stress element. So, and this is a part of some bigger mesh, and the coordinates of this uh, are given, and we have to, and also the nodal displacements are also given. So based on that, we had to like find out various things: stiffness, stresses, strains, and like extrapolating the stresses from the Gauss coordinates to the node one. So these things we had done. This I think this problem probably you cannot do it like if you don't know coding. Like it will be very difficult to do it with hand. Uh, like it will take a lot of time. But this is also this is the problem, and this is the code for that. So so first, like as I have said, like you have to like in Python, you have to define like this step. You can skip in MATLAB because you don't need to tell like what to use. So, but you have to know what which functions which you are using. But in Python, you have to tell Python that I'm using this library. So if I'm using this library, like if I define this, if I define import numpy as np, so NumPy has a lot of functions which I can use for array calculations or matrix calculations. So I can directly use NumPy and its functions, which are already defined in NumPy, for my help and solve the problem. So that's why I'm using NumPy here. You have first we have to import NumPy, and these are the different uh, parameters which are given: thickness, Poisson's ratio, and the thickness of the element. And these are the coordinates of the element. So from nodes 1 to 4, this is a uh, simple like regular geometry, quadrilateral, square quadrilateral, so with 4 nodes. And these are the displacements which are given. So like after the element, like after like there is after some load is applied, or like after some deformation has happened, this is the displacement which comes. Okay, so that is given here. So and like we want to use, like they have told us to use this Gauss quadrature integration. So there are like Gauss quadrature point. Like if you are using 2 cross 2 Gauss quadrature, Gauss agente or Gauss quadrature integration. So we have 4 points which we can get for two-dimensional domain, which is minus 1 by root 3 plus minus 1 by root 3, then 1 by root 3 minus 1 by root 3. So all these points are defined here. So these are all the Gauss points. So and then we have the shape functions. So shape functions are these, like we have already seen this today. So 1 minus z into 1 minus eta into 1 by 4. So these are all the shape functions in the natural coordinates, and this is the differentiation of the shape functions with respect to eta and xi and eta. So then after that, like I'm defining this as a function because I'll call this multiple times in my code. So after doing, like after calling this function for some point xi comma eta, it will give me the shape functions and also the derivatives at that point. So and this is my constitutive matrix for plane stress. So this is E, and then we have to, like when I want to, like if I want to get the stiffness, probably like stiffness terms, I should know B. Like we know that K is equals to B transpose T into T, something like this you will get. So B is something which we have to get. B is nothing but this uh, uh, this B is a matrix which contains this differentiation with respect to xi and eta. So, and also there is Jacobian. We have already seen the importance of Jacobian in today's class, and this should not be zero at any point in the domain. That is also something which we have seen. And so we will also need the determinant of the Jacobian and also the inverse of the Jacobian. So you can see that I'm using this np dot lean alg. So this is a linear algebra. Uh, uh, this is nothing but linear algebra. In NumPy, there are some functions which we can use for which we can use for linear algebraic operations, like finding a determinant and also finding an inverse. So I can use this np dot lineal dot get j to get the determinant and dot inverse to get the inverse of the j matrix. So in this uh, after that we have to get the dz and uh, uh, dn by this differentiation with respect to the local coordinates or the natural coordinates xi and eta, and we will stack this vertically. So dn by theta, and this is nothing but the derivative matrix with respect to xi and eta. And then I want this matrix in terms of the local coordinates or the not the local coordinates or the Cartesian coordinates x comma y. So I can get this by using inverse of Jacobian and again multiplying this inverse of Jacobian into our differentiation matrix for the local coordinate. So I'll get a 2 cross 4 matrix, 2 cross 4 matrix. So then after that, I can I can get my B matrix by using these lines of code. So we know how we can get, like you can refer to the previous class, like how we can get B from the strain displacement relations. So that is what I am defining here. So as I said, this matrix contains nothing but the differentiation with respect to differentiation of the shape function with respect to x and y. So this function, whenever I call, it will give me the B matrix, Jacobian, and the determinant. Okay. So then after that, I have to compute the stiffness using the Gauss quadrature rule. So because that has been asked. So in this, so for any point, like if you have, like I'll first start defining K as a zero matrix. So 8 cross 8 matrix, because I have 4 nodes. Let's say 4 nodes for each element, right? Like uh, this element has 4 nodes. So each node has 2 displacements with respect to like x and y. So I'll get total 8 displacements in x and y, u and v. So that's why I'll have my stiffness matrix 8 cross 8. So then after that, for each Gauss point, I can get this stiffness matrix, derive this stiffness matrix by using this lines of code. So and for after getting the stiffness matrix for each Gauss point, we can use our Gauss quadrature rule. So that is W1F1 plus W2F2 plus W3F3, and get our total stiffness matrix for the element. So that is what we can do here. So this function, this for loop is doing that. So first I have to get like there are a lot of different questions which are asked in the code. So they have asked to evaluate V at the nearest Gauss point to node 1. So for the nearest Gauss point to node 1 is -1 by root 3 and -1 by root 3. So if I use this B matrix and substitute the Gauss point which I have to calculate, you will get B at node 1. So the matrix B at node 1, and you will also get the Jacobian, and also you get the determinant of Jacobian. So they have asked to get get the element 3 comma 4 in the B matrix. So as I've said, in Python, indexing starts from 0. So 3 comma 4 means in this matrix you have to get 3 minus 1 and 4 minus 1. So that will give you from this matrix. I want to extract the uh, node 3 comma 4. Then after this, I also want the 4 uh, uh, 4 comma 5 element 4 comma 5 in my stiffness matrix, element stiffness matrix. That also can be like, because I have already got the element stiffness matrix, from that I can extract it. So then they have asked already also to extract the strains at the nearest Gauss point. So that is nothing but epsilon is equal to epsilon is nothing but B into U. So we, as I've said, we have got this from the strain displacement relation B into U. So B is something which we have already got. So for node 1, B is already derived, like already calculated, evaluated. And if you multiply this with U, which is already given in the problem, so they have already given you displacements at the various nodes, you will get the strains at the Gauss points, or the Gauss point near node 1. Then we also want the stresses at the Gauss point near node 1. That is nothing but sigma is equals to D into epsilon. This is the constitutive relation or the stress strain relation. So using that, we can get the stresses also. So now they have asked like compute stresses at all Gauss points. Then you extrapolate these stresses at the Gauss points to the nodes. So for that we'll just get all the stresses at all the Gauss points. So like minus 1 by root 3, minus 1 by root 3, 1 by root 3, minus 1 by root 3. So 4 Gauss points will be there. You get sigma at all Gauss points. Like I'm just using the for loop and doing this calculation. And then after that, we have to get this n mat. Like to do the extrapolation, I have to get n matrix. So for each Gauss point, I'll have all the shape functions, evaluation of shape functions, and then after getting this n matrix by using this loop. So for each Gauss point, you will get this n matrix. One row you will get. So and get this n matrix. And after that, I want to extrapolate the stresses at my Gauss points to the nodes, so the actual nodes of the element. So that I can use by using this relation of n inverse into sigma at the Gauss points. So if I do this, I'll get what are all the stresses at all the nodes. So they have asked what is the uh, what is the uh, what is the stress, what are the stresses at node 1. So I can just get the first row from this matrix. That will give me all the uh, no all the stresses at node 1. So if you want node 2, you have to, you will just put in instead of 0, you will put 1 here. So this is the like problem we have solved using this Python code here. You can also do the same thing using MATLAB also, or like other programming languages to you, which you know, maybe C++ or C or Python, uh, or Julia also. Like Julia is also a language you can use. So B at this Gauss point, B matrix at this Gauss point is given here, and in this the third row, fourth element is this. So this is first row, second row. In the third row, fourth element, this is the fourth element. So that has been also printed here. So in the B matrix, third row, fourth element. And this is the element stiffness matrix 8 cross 8. And in this fourth row, fifth element they have asked. So this is the fourth row and fifth element. So this is the fifth element in the fourth row. So that has been uh, given. So this is the answer. Like assignment also, like previous week assignment answers are also given. You can cross check. These are the same answers which we are getting here. So strain at Gauss point near node 1. So this is the epsilon values. So epsilon xx, epsilon yy, and gamma xy. So and this is the strain stress at Gauss point near node 1. This is using again the constitutive relation. We will get this. And these are all the stresses at Gauss points, at all the Gauss points. Then after that, we do the extrapolation. We have seen already in the last class how we can do the extrapolation. And then get the stresses at node 1. So this is the stress, all the like different stresses in x direction, y direction, and also the shear stress at node 1. So this is how we can use Python to do the calculations, get our get our. So this is the problem which is given this code. So this problem is complete. This is the last assignment's problem, like whatever I have shown you till now. So this is this week's problem, the second problem which we have given, right? So they have given this problem on assignment 7. Yeah, this problem. For the four node quadrilateral element given in problem 1, this is a quadrilateral element. Find out the element stiffness matrix using isoparametric formulation. If the element is part of mesh discretizing a section of a typical dam, okay, this is something we ignore, but yeah. So E and the new values are given. Then you have to find out the element 3, 3 of the constitutive matrix. This is very simple. And element 3, 3, 1, 7, 7, 7 of the stiffness matrix evaluated at the Gauss points near 1, 2, 3 respectively. So, and element 2, 2 of the stiffness matrix of the element. So this is stiffness matrix at the Gauss points, and this is the stiffness matrix of the element. So we'll see, like I have written the code. So this is the code. So as I've said, like we have to use some kind of libraries whenever we are using Python. So here there are no symbolic calculations which are required, like because I don't want uh, any symbolic uh, output. So I am just using NumPy here. NumPy is the only required library, and this is also something which we can use to print like some function. Uh, Even if you don't use this, like it's not a problem. Like, but this is the material properties which are given. So they have given in GPA. We have to convert this into Newton per meter square because unit should be consistent, and nu is 0.2, which is uh, our Poisson's ratio. So because they have told that the section is a part of a dam, the element is part of a section of a dam. So for dam, like we have seen that dam is a very long structure. Like so, for that we can use plane strain idealization. So for that we'll get this. This is the constitutive matrix. Okay, so this has already been derived. I think in week 5 or week 4. So that you can check. For plane stress, this will be different. For plane stress, this will be different. Because by using this constitutive relation, we can relate stress and strains. Okay, and these are all the coordinates. So this element which has been given, this element which has been given in the Cartesian coordinates is a distorted element. But I would like to make it a regular geometric element by mapping and by using isoparametric mapping to a natural a square quadrilateral which has a regular shape, so that my life becomes easier to do the integrations and all. So first we will see, we'll define this square, and this is the thickness which they have given. Let's say this, let's keep it 1 because uh, 1 meter let's say one, like you take, because we want to get, like whatever we get, we will get it for unit meter or unit length. So we will keep it, uh, we'll keep it 1 meter here. Okay. So because dam is a very long structure, uh, we can just tell that this is the stiffness per unit meter or per unit length, like that. So we already know the shape functions for the natural coordinate system for a very regular quadrilateral like this, a square quadrilateral with four nodes like this. This is the shape. These are the shape functions. So, and for this, we can also build our uh, uh, what do you call this? B matrix. So this B matrix is also can be uh, B matrix can also be built. So, but we need to first uh, convert, like we need to get the mapping from x and y coordinates to xi and eta. So that has to be done. Then after that, we can get the B matrix. So B will give me the strain displacement relation. And we should also have this Jacobian. So inverse and like inverse, and also the determinant of Jacobian is required. So inverse is required during the mapping, and determinant is required while we do the integration for k. So those are all the things. And again, we are using the 2 cross 2 Gauss quadrature rule here, because there are like 4 points. So and for each point, this is the weight, and Gauss points are this, uh, like I am using A and like then defining it like by, but you can also write -1/√3, -1/√3, 1/√3, -1/√3. That also can be done, but this is a simpler way to do it. And because they have asked the stiffness matrix at each uh, at each Gauss point. So at each Gauss point, the stiffness matrix can be evaluated by this function. Okay. So this is the uh, this is the evaluation B transpose D B into det J into T into W. This is my KGP, or stiffness matrix at each Gauss point. So if I take stiffness matrix at each Gauss point and sum it up, like for all the Gauss points, I'll get the elementary stiffness matrix. But this, for the time being, this is just the stiffness matrix at each Gauss point. So I'll get I'll get stiffness matrix at all Gauss points, and I'll store in some array. Okay, so KGPS will have four, because we have four nodes, so or four Gauss points. So KGPS will take stiffness matrix at first Gauss point, second Gauss point, third Gauss point, and fourth Gauss point. And because I also want the full stiffness matrix of the element, I can just take the sum of all the sum of all sum of all the stiffness matrix for all the Gauss points. So that's what we do, right, in Gauss quadrature integration. So they have requested these outputs. So in D, we want 3,3 matrix. That is what they have asked. So because we have defined it in meters here, meter square. So and something in the question they have asked in mm square. So you can do the calculation uh, by dividing it with 10 to the power of 6. You will get as I said, like in Python, indexing starts from 0. So if you want a 3,3 element, so in the D matrix, you have to index like this. So 2,2 will give you the 3,3 element in the matrix. And then they have asked what are all the uh, stiffness matrix at each Gauss point, and in that matrix some element has been asked. So all those points have been evaluated, and then 1,1 matrix element of the full stiffness matrix is also asked. So this is how we can use Python. So you can see like simple I don't know how many. Yeah, 88 lines of code has been used. You don't but yeah, I would suggest you please write the code. Uh, Probably take inspiration from this code and you can write. But you can also like just uh, I don't know but while you are learning, I would suggest please don't use chat gpt or something like this, because that will destroy your learning experience. So uh, you have like try to write it on your own. Like if you get any errors, go and check with some ai helpers like perplexity or chat gpt, then correct it and try to write it on your phone. Then only you will learn. Like you have to know each and every line in the code. So that's how we can solve the third problem in the assignment. Okay, not the third, the second problem in our assignment, week 7. I won't run this because this will give you the answers. Uh, then no point of me like you solving the assignment, right? So, but you can write a code like this on your own and you can do it. If you want to do it by hand, like it will take a lot of time, go and sit and do it. That is also your uh, option. That is also an option which you have. Okay. Uh, did something make sense? Like how you can use Python to your advantage? Uh, was it helpful?
It was helpful, sir.
Yeah, yeah. Anything? Do you have anything to ask, or else we can close this session for today? We are past time. Anybody have any questions? Shashidhar, you do coding? Shashidhar?
I use MATLAB for doing.
Okay. Okay.
Python, I am not aware.
Yeah. Yeah. Like, both are like very similar. There are some differences you will see, but length of the code will be almost same in Python and MATLAB.
Okay.
Yeah, obviously you can use Python or MATLAB, whichever you use. But for symbolic calculations, Python is very good. Like you can see print, you can print like this. Uh, Very good looking. Like this is like textbook kind of printing that you won't be able to print in MATLAB. Like you have to get like install LaTeX and do in some tools with respect to LaTeX and do it in MATLAB. But here you can do. This is a simple expression. You can also uh, print like this and see. But if you have a big expression, then reading it will be difficult. If you have some kind of printing like this, like if I just run this. So in MATLAB, if you run, like you will also get this kind of output. Like you have to read something like this. So it becomes difficult to read. Like if you have a very big expression. So in Mathematica and Python, you can print something like this, like very aesthetically pleasing expressions. So for symbolic, people use Mathematica or Python. So Mathematica is like widely used if you have the license because it is very optimized. Python is also good. Okay. Uh, if you have anything, you can ask. Otherwise, we can close today's session. Uh, we'll meet in the next week. Okay. Okay, guys. If you have anything, you ask me. Otherwise, you can leave.
Thank you.
Thank you. Thank you for joining. Night.